All right, here we go. Number 30. So 30 here, 1,300 kilogram roller coaster starts at rest at the top of a 60-meter hill. Track goes down to the ground before it go back up to the second hill with a height of 35 meters, assuming there's no friction here. Draw a picture and find how fast the coaster is traveling at the top of the second hill. Okay, so we've got a roller coaster starting at the top, going down, and then back up to a second hill. We're assuming there's no friction. Draw a picture and find out how fast the coaster is traveling at the top of the second hill. Okay, so we've got something like this going on. We've got kind of my first hill, goes down, comes up to a second hill, something like this. Here we'll call the ground. Here's my roller coaster starting up here, travels down that way, and then comes back up to this second hill and continues moving or doing whatever he's doing at that point. Okay, first hill is 60 meters above the ground. Second hill is 35 meters above the ground. Tells me that it starts from rest, and then it wants to know how fast am I going. So here, this velocity is going to be 0 at this point. And at this point, the velocity is, who knows, something. All right. So I'm looking at this, and I'm thinking to myself, all right, this is conservation of energy. I have some energy at this point, some energy at this point, and it changes in between those things. And conservation of energy is this one. This work equals change in energy. In other words, the work causes an energy change. Now, you're saying to yourself, well, there's no work being done. I'm just going. It says there's no friction. There's not, like, it's just moving from one place to another. Okay, let's look at the equation again. What if there's no work? If there's no work, the change in energy is 0. Which means the energy just switches between kinetic and potential. It's still there. It's still the same values. It just changes how it is distributed between those two types. So this is the equation I'm going to be using, this one that's got all my kinetic and potential stuff. The thing I'm going to have to keep in mind is because there's no friction, I'm going to write down that W equals 0. And I'm writing this really big here because I want to make sure I'm not getting that confused. So there's no work at all in this problem. No friction, no, like we're not worried about any work done by anything. Okay? So let's write down the things that we do know. Okay? Well, we know the mass of the roller coaster. Mass of the roller coaster is 1,300 kilograms. Okay, we know it starts from rest. We know it ends up at some speed that we want to solve. Then we get to the heights. Now, there's going to be two heights. There's going to be a height initial, where I am at the top. And there's going to be a height final, where I am at the second hill. Now, you can absolutely use 60 and 30 here. You can absolutely use 60 and 30. 60 would be the starting point. 60 and 35. 35 would be the ending point. Totally fine. That is what I'm going to plug in. But there is another way to do this. Some of you may look at this and be like, oh, well, I could talk about how high it is above the second hill. So I could call that my height of 0. Or I could call the ground 0, either way. If I called the height 0 at the second hill, then H final would be 0. And then my HI would be, how high is 60 above 35? Well, it's 25 above that. Now, for some of y'all, that's confusing. And if that's confusing, just make the ground 0. Make H 0 on the ground. In which case, HF is still 35. And in which case, HI is still 60. I don't care which way you do it. It doesn't matter for the problem. Doesn't matter at all. I don't care. Whatever works for you. Whatever makes the most sense for you, whatever you're able to do the easiest. Okay? I'm going to do it the purple way, but just know the pink way will give you the same answer. The pink way is actually mathematically a little easier. Okay, so here we are. Work equals KF plus PF minus KI plus PI, so work equals delta E. Okay, I don't have any work, so that's 0. Now I need to plug in all these KE, PE business. So KEI, that's my initial kinetic energy. So kinetic energy is 1/2 mv squared. So 1/2 mass initial velocity squared, which is just 0. Now I need my PE initial. PE is mgh. So mgh. And again, I'm using my purple ones here. The pink ones, if I was using the pink numbers, I'd just use 25 instead. Okay, and when I plug that in and solve, I get 764,400 joules. Oh, did I put this in the wrong spot? I did, didn't I? Yep. Sorry. This is the finals. I should be putting the finals here. There we go. That's my bad. Hey, be careful. I made the mistake, so it's easy to make. Okay, then we do the finals here. One-half mass final velocity squared. I don't know what it is, so I just leave it as VF. Half of 1,300 is what? 650. 650. And then we get VF squared. Okay, can't do anything else with that. And then PE final would be M G H. $445,900. And then we just solve from here. Okay? I'm going to go ahead and subtract the 650 VF squared to both sides. The reason I'm doing that is I'm just trying to get all my numbers on one side, so I'm going to get that to the other. So we get negative 650 VF squared equals, and then these two numbers we can subtract, right? 445,900 minus 764,400. So I'm going to subtract those two. Gives me negative 318,500. My negatives will cancel. I got a negative on each side, so it cancels. Divide the 650 to both sides. That gives me VF squared equals 490. I don't want VF squared, I want just VF, so I square root that. Should be 70. And VF squared, sorry, just VF now that I squared it would be 22.1. Okay. Any questions on that one or that setup for that?